Good evening, class 11. Let's start. Le Chatelier's principle. If a system in equilibrium is subjected to stress, that is change of temperature, pressure or concentration, equilibrium shifts in such a way so as to undo the effect of the stress imposed. Let's apply Le Chatelier's principle to explain the effect of change in concentration, pressure, temperature to various reactions. First is effect of change in concentration. So according to this principle, increase in concentration of any one of the reactant shifts the equilibrium to the forward direction, while increase in concentration of any of the products shifts the equilibrium to the backward direction. For example, Fe3 positive, SCN negative. These are the aqueous solutions. We get a complex that is your Fe, SCN, 2 positive. This is your blood red coloration. Now here, if concentration of Fe3 positive increases, suppose if we are adding externally some ferric salt, ferric chloride, okay, then what will be happening? This Fe3 positive concentration increases and the reaction will be shifting towards forward direction. Okay. Next, if potassium bifluoride is added to this solution, if I am adding KHF2, then what will happen? This ferric ions will be forming complex. It is FeF6 3 negative. Then what will happen? On adding potassium bifluoride, concentration of Fe3 positive decreases. So what will be happening? The reaction will be moving towards the left hand side, that is towards the backward direction reaction will proceed. Okay, this is about concentration. Next we move to temperature. Reversible reactions which are exothermic in forward direction are endothermic in backward direction. With rise in temperature, the reaction will shift to a direction which involves absorption of heat, that is backward direction. So if I take the example of an exothermic reaction, the common one is the Haber's process. This is the forward reaction is exothermic and backward reaction is endothermic, definitely. So what will be happening? With rise in temperature, the reaction will proceed to that direction which involves absorption of heat, right? So if I increase the temperature, then this reaction will be proceeding to the backward direction. And if I do the reverse, if I decrease the temperature, then the reaction will be moving towards the forward direction. Okay, so now we come to effect of change in pressure. Now change of pressure will have no effect on the state of equilibrium if system does not involve gaseous components, and the next one is number of moles of gaseous reactants is equal to the number of moles of gaseous products. That means if delta N is equals to 0, then there is no change, no effect of the change in pressure. And next, if system does not involve the gaseous components, that in that case also the pressure, the effect of pressure will not be applied. According to Le Chatelier's principle, on increasing pressure, rate of the reaction will increase, which causes a decrease in pressure. On increasing pressure, volume decreases, hence molar concentration increases, because volume, molar concentration is equals to N by V, C equals to N by V. So molar concentration increases. To undo this change, the reaction which produces lesser number of moles of gaseous substance will be increasing. If I consider your Haber's process, in forward reaction 4 moles of reactants are changed into 2 moles of product. That means left hand side number of moles are greater than the right hand side. Okay, so what will be happening if I increase the pressure over here? If I consider Haber's process and increase the pressure over here, my volume decreases. If volume decreases, molar concentration C increases. If C increases, N increases, that is number of moles increasing. So the reaction will be shifting to that direction which involves lesser number of moles. So if I consider this particular reaction, my reaction will be shifting to the right hand side if pressure is increased. Okay, and vice versa if pressure is decreased, definitely. Now next we come to effect of addition of an inert gas. Now if an inert gas like helium, neon, etc. is added to a system at equilibrium at constant volume, the total pressure increases. However, there will be no change in the position of the equilibrium even though the pressure has changed. This is because the concentration of the reactants and the products, that is ratio of their moles to the volume of the container, will not change. Hence, values of concentrations will continue to satisfy the equilibrium law. Consequently, the reaction quotient will continue to be equal to Kc, and no changes in the amount of the reactants or products will occur. Next, when a gas is added to a system at equilibrium, keeping the pressure constant, the volume of the system increases. This results in decrease in the number of moles of the gas per unit volume. Hence, equilibrium shifts in a direction in which there is increase in the number of moles. So, reaction with delta N positive. Three conditions we have: delta N positive, delta N negative, and delta N zero. Okay, so reaction with delta N positive will shift towards the forward direction. Okay, reactions with delta N negative will be shifting towards the backward direction, and delta N zero remains unaffected. Okay, now last one, effect of catalyst on equilibrium. If a catalyst is introduced in the system at equilibrium, there is no change in the state of equilibrium. This is because catalyst increases the rate of forward as well as that of backward reaction to same extent. It simply helps in the early attainment of the equilibrium state. Okay, so that's it, class 11. Thank you.